Since 2023, Florian works at the RWTH Aachen in Germany as a junior professor in the field of molecular structure of condensed matter with large data. Since 2021 up to 2023, Florian worked as a postdoc at the University of Regensburg in the field of method development for the analysis of X-ray diffraction and absorption data. He also works since 2019 up to today in the OLEX company at the Regensburg as a software developer developing OLEX2, Nosfera 2A2 and LabSEF modules. Within the years 2019-2021, Florian was a PhD student at the University of Bern and Ariel at the University of Bremen, both in the group of Professor Szymon Grabowski. Florian got his bachelor and master degrees from the University of Bremen under the supervision of Professor Szymon Grabowski, and then he started his PhD and moved with Szymon to Bern. Florian worked at different synchrotrons such as ECRF, APS, or Spring 8, and is known from his programming skills. For last year, Florian started ambitious young group of researchers enjoying quantum crystallography science. Today, Florian will talk on enabling everyday chemical application of quantum crystallography, spin state determination, and fast result. Florian, the screen is yours.
Thank you very much for the kind introduction, and thank you for having me. It's very, very, very great to be able to give a lecture in this already very long-standing series. As you can see on my title slide, it's already the 52nd lecture, and when I was still watching them online as the young postdoc, I was always fascinated to see the science presented there. So it's a very great pleasure to be here and present a little bit of what we have been up to in the last 2 years. So to begin with, for anybody who is not yet familiar with the concept of what we are doing and what I personally try to contribute to the field of quantum crystallography, I'm mostly involved in a software called Nosferatu, which is the non-spherical atoms in OLEX2 interface, which can be basically summarized in this one slide. So in general, OLEX2 is the workhorse and the graphical user interface that you as a scientist or as a user from a programming perspective are presented with. And it basically handles all the difficult things like input selection, structure growing, visualizing, and the refinement of your crystal structure, while we neatly hid away all the difficult bits about software interfaces that you might need to do for this to run, like quantum mechanical softwares and partitioning softwares that you need to get non-spherical scattering factors on the fly in the background. So OLEX2 itself then calls quantum mechanical software through the delivery of a CIF file or an XYZ file, which delivers an output wave function, and this wave function can be used to be partitioned into atomic contributions. As you can see on the right-hand side, our structure factor equation is atomic contributions. We sum over each individual atom J. In principle, if you wanted to draw this out, the different areas of work that need to be done can be distinguished as the OLEX2 part, taking care of the individual atomic position, the R vector, and the displacement parameters, while the QM software and the partitioning software in this non-spherical atom interface take care of delivering the atomic scattering factors. It should go alongside this note that we are by far not the only one doing this. For example, there is an implementation of periodic wave function calculations for this procedure developed by Paul Niklas Ruth. There is ELMOHA, which is even older than Nosferatu, which was done by Lorraine as an interface to bring extremely localized molecular orbitals into the refinement. There is fragmentation approaches, one, for example, done by Justin Bergmann, but also one done in Warsaw. There is different partitioning schemes extensively analyzed in the group of our hosts, which was published in IOCRJ 2020 and a further update on 2025. And I think this is a point that needs to be made. There's more in the making. This field is ever improving. So keep an eye open in the literature. As I'm speaking today, maybe next year already, new partitionings, new ways to think about this problem might have emerged. So this field is evolving, and it's very, very interesting to see what it can do. But if we want to bring it back to the, let's say, how my students would say, old school style of the original implementation back from 2021, the improvement that we can do if you have a good data set with strong and sufficient resolution data, it is no surprise nowadays to see residual density left from the diffraction experiment on the interatomic bond axes. So like we have here in this example structure of ibuprofen back from my PhD thesis, you can see that the residual electron density mainly resides on the bond axis, and that this is information to me as a chemist that I could explain. Why is that so? Because we are using the spherical atom model. The spherical atom model does not attribute any charge redistribution. It does not attribute any interaction between atoms. Each carbon is exactly a carbon copy of the other one. So what this leads to is a very frustrating fact that if you measure better data, you will get worse R values in the refinement in the end. If you have such good data that the noise level is below the level of chemical information contained in your data, you will start seeing worse agreement statistics if you refine them using spherical atom models. So if you use Nosferatu on this data set, this is what it looks like in the end. The residual density map is more or less clean. If your screen and my internet connection are good enough, you might see some green specks over here, which are the leftover at the same ISO value that I presented on the left. So the noise level in residual density has decreased from 0.8 electrons per cubic angstrom to 0.3 electrons per cubic angstrom, and the R value has come down 1.5%. But the R value itself is not really telling. What convinces me is the explained electron density in the bonding region, because this to me now has nothing left that I could explain just by looking at the bonding picture. What else do you get? So one of the big advantages of this technique is that even with X-ray data, even with, let's say, medium resolution, 0.8 angstrom resolution, X-ray data, you can get hydrogen atom distances refined to the correct distance when compared to neutron diffraction results. So if you refine them freely in the spherical atom model, all the hydrogen element distances are slightly too short. And if you refine them using the non-spherical scattering factors, they move out to the correct distance. The second effect you observe is, if you pay close attention, what you can also see, the uncertainty of your refinement naturally has to decrease, because thinking about what the R value actually means, it's the residual that is left in the least squares procedure. So if we have overall better agreement in the least squares procedure, because we take into account more effects that are present in the data, the mathematical uncertainty in what we refine needs to decrease. So the overall certainty that we can make on bond distances, bond angles, and everything else will be better if we use non-spherical or chemically reasonable scattering factors. Of course, people have done this, as they say, standing on the shoulders of giants. There was a lot of research being done, for example, by Magda Wojinska, when she compared over 80 structures of neutron diffraction data and small organic molecules in this article. And also I was lucky enough to be part of a team that looked at a comparison between X-ray and neutron coordinates, and they agree more or less. What I want to introduce now for a later part of this presentation is two nomenclatures, I like to call them. So one of them is that I want to summarize these values, like the R value, the residual electron density, and the overall agreement of the measure data and your model data. I want to call them the electronic figure of merit. So anything that has to do with the intensities that you measured and calculated using your model will be summarized in one value that we call the figure of merit for the electronic agreement between your electron density that you model and that you have in your data. And the other name I want to introduce is this weighted root mean square displacement of interatomic distances. So the agreement, let's say, geometrically speaking, because an R value gives you no idea how good your interatomic distances are. The R value can be as great as it is. Your interatomic distances could, by coincidence, just be wrong. So we want to introduce a two axes kind of discussion, one about the structure and one about the electronic properties of your model. When I usually talk about this, what happens next is people ask me, well, that's great, you can do it for organics. What about something heavier? So then usually what I do is I show them this paper where we recently looked into some compounds that contain neptunium, which has been the heaviest element that I treated using Nosferatu so far. We had to include new basis sets in order to treat it correctly, but you can even refine neptunium containing compounds where you have a hydrogen atom protonating one of the ligands. I mean, you could see that it is protonated from the bond angle already from the data, but we were able to refine this hydrogen position using Nosferatu on this compound. So I would say anything that is stable enough so that you can work on it with a reasonable timescale on your X-ray diffractometer can be treated using Nosferatu if you are willing to invest maybe a few minutes into getting the correct basis set into the refinement. Going along that line, my students here in Aachen started to play a little bit with Nosferatu also on transition metal compounds. And one of the compounds that ended up on our diffractometer was more salt. It's iron hexahydrate, and it's iron 2 with sulfate and ammonium counter irons. And the interesting, let's say, feature of this data set was that we measured fairly high resolution data on this compound, and we did Nosferatu on it, and it looked horrible. Why is that? So back in the time, my student just quickly went through the data reduction and data refinement because we were having renovations in our original labs and we were in a different room and everything was messy. So we didn't have time to really closely think about all the analysis, and we just wanted to see if the data set was useful. And then we had this blob of residual density around the iron atom. And initially we thought, well, that's odd. Can we not do d orbitals correctly? And then we sat down again and we thought, well, wait a second, this is iron 2, and iron 2 is notoriously known to have a high spin and a low spin form because we have a d6 system. So we calculated what would be the difference between the electron density of a high spin and a low spin wave function on this fixed geometry using ORCA. And if you look at that, I would say that's pretty close to what we see in the residual density. So what happened was, in the default mode, if you operate Nosferatu, he will always choose a low spin state because it's easier to guess a low spin state than it is to guess a high spin state correctly. So Nosferatu by default assigned the system a total multiplicity of 1, which is the low spin form. But in fact, if you look at the refinement of the low spin form, you have this strong residual density at the iron center. And if you refine it using the high spin wave function with a multiplicity of 5, you are very, very happy because all the residual density is gone. It was even so strong that the R value of this structure of the low spin wave function in this case was worse than the independent atom model, the spherical atom model. So you had even worse R values if you used Nosferatu. So I can understand if people would get upset if they use Nosferatu, spend the time calculating the wave function, and then getting worse results. But it was interesting because this is now a unique way to unambiguously determine which spin state your metal sits in. So you can just, from comparing the two spin states against your experimental data, say which one it is based on the electronic agreement. We, of course, repeated this on a low spin compound as well, which works as good as it does with the high spin iron center in this case. So if you want to do this, feel free. If you need more details on how we actually did it with the different comparison of the models, here is the reference. I think this is a very, very nice application of how we can use it. Then, after the renovation of our labs was done, we were fortunate enough to get our hand on a new diffractometer, a very, very great new diffractometer. And just directly after it was installed, we had an institute excursion, which was inviting for my student, Daniel, to start up a measurement that he said, okay, let's see what we can tickle out of this machine. So he put a crystal on, and he said, okay, we have 20 hours until tomorrow when we are back from that excursion. And we measured a data set with a multiplicity after outlier rejection of 37.2. So modern diffractometers can actually give you quite a large amount of data that you can work through. Additionally, we ended up with an average I over sigma of approximately 100 at a resolution of 0.55 angstrom. So I would say this is a decent data set. This decent data set has good statistics over the whole resolution range. So we have good agreement statistics and strong intensity even at the outermost resolution shell. And the residual density after the spherical atom model is, as you expect, on the bonds in the lone pairs towards the central iron. And the R value of 2.5 told me that this is a data set where we can maybe work deeply with Nosferatu. So we did it. This time we were sure it is a low spin wave function. So this time it is iron in a low spin state. And we were presented with some residual density left there. I mean, the R value 1.25 at a resolution of 0.55 angstrom is not too bad. But this got us a little bit suspicious. So Daniel and I had a look at this and maybe said, okay, what if there is a second iron disordered in there somehow? So we started making a disorder model. And of course, you start entering the regime of fitting the elephant. If you see such a residual density and you start building disorder models. But then Daniel told me, well, of course it is a disorder model. Look at the literature. We found this paper, and this compound is a known spin crossover compound at a temperature where the spin crossover happens at this, let's say, medium temperature. But even at the fairly low temperature we measured at 140 Kelvin, we are still left with some maybe small percentage of the other compound. So we got interested. So what if we build a model where we have a high spin and a low spin compound next to each other, and in a collaboration that I had earlier on about combining the multipolar models from the MATS data bank and Hirschfeld atom refinement, we had a hybrid mode available in OLEX2 where you can combine different calculation procedures of different parts of the structure. So we said, well, what if we use this, do two calculations, one high spin, one low spin, and refine them as disorder across a high spin, low spin transition. So we did first some experiments at the Rossendorf beamline at the ESRF, where I can see our host Krzysztof Wozniak is residing at the moment, because I know this background of the guest house at the ESRF by now quite well. And at Christoph's beamline, we measured very good single crystal diffraction data across a large range of temperatures, and we were able to refine the occupancy of high spin as a function of the temperature. And if you compare this to the plot of the literature known spin crossover compound, I would say this is convincing. But I have to admit, traveling to the synchrotron every time to measure this data is maybe not the most energy and resource conserving endeavor. So we tried it again at home. And on our new diffractometer, we were able to measure this temperature series as well. And we could also refine the occupancy of the high spin compound very easily as a disorder model across different temperatures. And the nice thing is, at home, the pressure is a little less because you are not wasting precious beam time on a temperature series that you can more easily do at home, let's say. So we asked ourselves, this is maybe just a lucky shot, because, for example, this got us a little bit worried. It should not decrease after the spin crossover. So what is going on there? How big is the uncertainty of the refined occupancy? Because the least squares uncertainty is definitely not the sample uncertainty. So we tried to redo these measurements. And we did measurements on 4 different crystals. So we repeated 2 temperature points using 4 different crystals. And the scale here is, of course, a little bit bloated up, but let's say within a regime of 1.5–2% error, we can refine across different experimental settings with different crystals. We can reproduce the occupancy of the high spin component before the spin crossover, and over here we have slightly more 2-ish% error on the occupancy. But this was reassuring, because if you follow across the spin crossover curve, this is more than enough accuracy to actually follow the trend and maybe follow spatial resolution of things. And then knowing what we do here in Aachen and knowing the title in my denomination of my position here saying big data, we also try to do different comparisons with different levels of theory, trying to get a feeling for how big is the influence of the theoretical level on the data. And we ended up seeing that there is actually also some damage that you can do if you choose wrong functionals for the refinement of the occupancy. So you have to be careful. For example, Hartree Fock is always a little bit an outlier. Let's see if we can see this as a re-emerging trend. Because this was so interesting, we wanted to see how far can we push our new machine. Our new machine was tasked to do an entire temperature series in one go. We had this compound. It is ethanol solvate in the crystal and some compound where we have the low spin form, and then at 10 Kelvin steps, 7 temperature steps, this is the high spin form, and then we went down to 100 Kelvin, and these 7 measurements were done in 67 hours. It was not garbage measurements. It had a multiplicity of 12 after outlier rejection, and the I over sigma was 100. And then, since the crystal was sitting there on the diffractometer for quite some time, it decreased to 70 at the lower temperature. But the resolution we got across all these measurements was still high enough to be satisfactory at 0.5 angstroms. And this was an interesting compound because we looked at this compound and we refined the high spin occupancy again as a function of temperature. And then we saw this dip somewhere in the middle. And I know one gentleman in the audience that I saw earlier appear, the name in the audience, would say, of course you did, because back in 2003, they already analyzed this. And this specific point is where you have an intermediate phase where you start a superstructure appearing, start seeing a superstructure appearing, where you have the ordered high spin, low spin compounds next to each other. And then you have a superstructure for some Kelvin, and then you start seeing the normal model again. So this is, of course, after the analysis using only one lattice to basically iron out overall data. So this dip is an artifact. If you treat it properly, like they did in the 2003 paper, you see this ordering. So you can apply quantum crystallographic methods like non-spherical structure refinement to see, for example, chemical bonding features like the ligand metal interaction developing as a temperature series, or if you start comparing these things where the spin crossover point is from diffraction data. So this is already quite convincing. But what bothered me quite some time was the question of which functional, which basis set, which setting usually gives you the best results. So this brings me to the story of the never-ending calculation. Since Daniel is my first PhD student, he had to suffer through all these wild ideas the most. Basically, what I told Daniel to do is, can you not try all of them? And he did. But he didn't do that alone. We had a little bit of help in a collaboration with Florian Meurer from the University of Regensburg, who developed a plugin for OLEX 2, which is called Sisyphos. Sisyphos can basically do a lot of data analysis without you having to actually click buttons. So you select what you want to do as a, let's say, job list, and then you just let him do his thing. And in the end, you get a nice summary of results. So using this plugin, we were able to do the systematic permutation of all parameters in Nosferatu, all the basis sets, all the functionals, all the convergence settings, all the integration accuracies, solvation or no solvation, local dispersion correction in the calculation. And this was done in a series so that in principle there were 14,112 refinements per structure. This leads to a lot of data. So we couldn't go with big tables and analyze them all by one, because we had 32 benchmark structures so far. This is too much data to be analyzed in a big table. So we had to think of a way to summarize this. And this is where the nomenclature I introduced earlier comes back into play, because what we did is each refinement, each of these data points is now plotted on a two-dimensional plot where we say in the X direction, we plot the structural agreement with neutron reference data, and in the Y direction, we plot the electronic agreement, so the R value and the residual density. And we renormalized it, which is why we call it a star here, so that the average of all calculations that we ever did in this study is at 0, 0, and anything that is negative in any direction is better than the average, and anything that is positive is worse than the average. So what you can see is that this data clusters a lot around the average. So even if you choose something that is not really ideal, you still end up somewhere among friends. There's only a very few outliers out here that are doing something really, really bad. We will see why that is the case later on. But if we, for example, look at the ranking according to the functional or method for the calculation being used, we see, of course, blib, TPSS, these older functionals, they are approximate. They cannot perform as good as modern hybrid functionals can. This is no surprise. Then we have the, I always call it my arch nemesis, B3lib. B3lib is a well-known functional to give you good geometries if you do a geometry optimization, but if you need the electronic density of a system, it is known to be suboptimal. B3lib, I wouldn't go there, because for the same calculational time of B3lib, you can get much better functionals. However, local density approximation, if I talk to my people over in the physical chemistry department and tell them that local density approximation is among the mid-range, they would tell me to leave immediately, because this shouldn't be the case. But the density that you get from these methods is actually not too bad. It's the energies and other features that are not good. Of course, omega B97X or PBE0, they are very, very good functionals. They will give you good results. My personal big player in here is R2Scan, because it's a GGA. It's extremely fast, but it's still quite good. So better than B3lib. So R2Scan is a real bargain here. However, Hartree-Fock won. And this confused me. I told Daniel to check the data again and again. And he said, well, sorry, I can't do anything. It won. So let's keep that in mind. The next comparison you can do is, of course, trying to cluster the results by the basis set that has been used. And there we see why these ones are so strongly outliering everywhere. Because STO3G, how is that ever going to give a reasonable result? And 321G also is known to not be ideal. So it's no surprise that they are outliers. Then, of course, 631GD, I would say a medium quality basis set. It is quite okay in terms of the electronic structure, but it failed to reproduce the hydrogen distances accurately. So 631GD, I wouldn't go there. However, some other basis sets like DEF2SVP for the cost to result ratio actually surprised me. So DEF2SVP for these small organic test structures that we did was actually very, very good. So it's not always that you can throw a lot of P's and a lot of T's on your structure and get the best results. Sometimes it's somewhere in between. Sometimes your data is just not so good that you see these minute details that the triple or quadruple zeta basis sets actually try to resolve. Another effect that needs mentioning is the effect of the environment. And I titled the slide, so should Hartree-Fock be used after all? Because so far what we compared was the interatomic distances. Let me talk about environmental effects as well. If you do Hirschfeld atom refinement using the molecular calculation that we usually do in our structures, you end up with the disagreement of the distance in carbamazepine of 4.3%. So it's still quite off. What people did then is try to include, for example, because this is a strongly hydrogen-bound system, they try to include the other part of the system, so the dimer calculation, which is basically just two molecules. And if you compare the time that you need for this calculation, you go from 18 minutes on, it's Bruno's laptop, it's not my computer. On Bruno's laptop, this took 18 minutes. For a full refinement iterative until full convergence was achieved. The dimer calculation needed 72 minutes. So it, of course, takes considerably longer time because you have to calculate a much larger system. And then what we did is, well, maybe the dimer is not enough because there might be dipole interaction with neighboring molecules that maybe have a molecular dipole that acts on this. So we started building a small cluster. And on his computer, this calculation took almost 1,200 minutes. So it becomes unfeasible for everyday use, I would say. And the new feature that we tried to introduce in our collaboration was a QMMM embedding method that the Orca people developed together with a former student of our group, Anneke Dittmar, who actually implemented a way to mimic the crystal field using embedding that is basically as fast as a more sophisticated calculation, because in the QMMM, this is the system that we modeled. There is a 12 angstrom radius around our central molecule where all molecules are still considered. And this took only 114 minutes, so slightly longer than the dimer calculation. What's the result now? Of course, these QMMM calculations, if you embed it correctly using the correct embedding, you can get quite decent results. But what was even more interesting is we were also able to compare the atomic displacement parameters using the similarity index. And what we see is that going from the molecular calculation to the calculations where we introduce the environment, for example, using this molecular embedding method, we see better agreement with the hydrogen atom ADP, slightly, but into the right direction. So why did I entitle this slide, "Should we use Hartree-Fock after all?" Don't think of the ADPs, because if you compare the ADPs now using different methods, Hartree-Fock clearly fails in getting the correct hydrogen ADPs. And for that matter, also all the other ADPs, because any of the atomic ADPs are damaged by using Hartree-Fock during the calculation. And it doesn't really matter that much which functional you use. All of them produce more or less reasonable ADPs in the end. So my take-home message from here is, don't use Hartree-Fock for everything, even if the interatomic distance is quite convincing from our benchmark paper. The ADPs are not so much. So this led me to philosophizing with my students. What could it be? What could be the reason for this? And we discussed that maybe the partitioning is to blame, because what we do at the moment is benzene will be cut into atomic contributions using the Hirschfeld-Stockholder partitioning. And the Hirschfeld-Stockholder partitioning is an assumption that in the theoretical chemistry community is, let's say, not the most welcome partitioning method that is being used. So there is others. And if you think about it, if you look at the difference between the electron density of a density functional theory calculation and a Hartree-Fock calculation, for example, along this carbon-hydrogen bond, the difference is this. What you have is, I did DFT minus Hartree-Fock here, what you have is in the bonding region, you have too much density in the Hartree-Fock calculation, and in the core region you have too few, because you're missing the effects of the electron correlation. And this effect, if you apply different partitioning, is of course divided differently into individual atoms. So for example, if you use Becker partitioning as a cheap alternative to Hirschfeld partitioning, you can minimize the overlap of this bond being attributed to the wrong atom, and therefore the hydrogen atom has significant influence depending on which partitioning you use. So this goes in line with, for example, the discussion in the IUCRJ paper from Michał Chodkiewicz on the exponential H, where they also said that the Hirschfeld atom partitioning is too diffuse. So I came to similar conclusions. And of course, if we have bonds that are being too electron rich and we have a too diffuse partitioning function, these two errors can cancel out because we basically swallow back up what was misplaced in the first place. So we are currently trying a different approach, the resolution of identity, which is basically a partitioning that is used in QM calculations on an everyday basis. You have these J integrals that you need to solve for the quantum mechanical calculation, and they have these nasty 4-center integrals. But in principle, if you have the overlap of two S-type functions, you generate something that is in between. And this something can, practically speaking, be summarized by a different basis set that is just a little bit more polarized. So you can approximate the J integral by introducing a different basis set that basically tries to describe this using a more, let's say, expanded basis set with more angular functions. Basically trying to compensate for this additional density by introducing P functions on top of the S functions and trying to swallow this effect. So what this basically means is you need to build a second set of basis functions that is more complex than the first one, and then you can just project the electron density down onto atomic centered orbitals. How do you do that? One way would be very familiar to this community. You minimize the error by least squares of the electron density. However, it was shown that this is very inefficient and this is usually very unstable in quantum mechanical calculations. And they basically said, why not minimize the self-repulsion of the error that you do? So what they do is they calculate this overlap matrix, and it basically boils down to a simple deconstruction of the density using Coulomb metrics. And this is basically what we are trying to implement as a new feature, which will come back later. So this basically is a different way to overcome this, let's say, cancellation of errors that we observed in our benchmark study. But then I have people in my institute which are less interested in the minute details of the structure, and they just want the best possible structure in the shortest amount of time because they need to publish and their supervisor is in their back, and they want results fast and ideally yesterday and ideally without thinking. So we started implementing features to make the calculation faster than these 100 minutes, because 100 minutes is a very, very long coffee break. So we tried to introduce, for example, theoretical methods that use effective core potentials. But when I was a student, I was told effective core potential basis sets cannot be used in the calculation because we need all electrons to scatter, right? Then why do we not introduce them? So the core valence split basis, the effective core potential basis set, has the missing structure of the electron density because we are missing the innermost electrons. But what if we introduce them? So what we did is we calculated the difference between the effective core potential electron density that you obtain for an atom and the all electron calculation if you use a relativistic full Hamiltonian. And then we calculated the difference and we said, well, maybe this is what we need to reintroduce. So we reintroduce core electrons and we reintroduce the error that was done during this calculation. And this basically leads to a procedure where we pre-calculate atomic densities. We calculate the difference between these two calculations. We fit the correction function and neatly this has an analytical solution for the Fourier transformation, so we can directly calculate the scattering factor from these correction functions. It's this equation if you fit it using Gaussian functions, and then you can just apply them to the scattering factors. So you're basically back in the game without having to worry about missing electrons in the core region of your effective core potential basis set. How and when can you use it? So the scattering factor of an atom basically becomes a sum of three contributions. The first contribution is the classical Hirschfeld atom partitioned, for example, scattering factor that you get from the ECP calculation. So in the normal procedure, you would partition the wave function as you do with an all-electron wave function calculation. Then you add a Slater-Korb density function, which has an analytic equation that you can use to calculate it, and then you can apply the correction function. This basically opens, for example, the world of the DEF2 basis sets. If you have Ulrich's DEF2 basis sets, they are defined as all electron basis sets up to krypton. And if you have an element above krypton, what you can do is you can use the ECP version of this and basically get all the way up to radon. Neptunium that I presented earlier, you still have to use a different approach, an all-electron relativistic calculation or something like that. But is it worth it? So does it perform? Does it compare? So we performed relativistic calculations using DKH Zora and all electron bases, and we tried to compare it on these three systems. They are basically a mercury and two gold systems, where we have, in the first case, one atom that has an effective core potential. Then we had 5 atoms with effective core potentials, and then we had symmetry grown, because here we have a mirror plane in the crystal structure, so it's only half. We wanted to have something where we have to play a little with the calculation as well. The all-electron calculation gave results of 1.7, 2.5, and 1.6 in R value, and the timing was 600 seconds, 80 seconds, and 150 seconds for one wave function calculation and a partitioning on my computer, I have to admit. And then we did the effective core potential calculation, and basically what we can save is approximately a factor of 3 in timing while getting identical results in terms of R values and residual densities. So the improvement is from a factor of 2 nearly up to a factor of maybe 3, depending on how severely your system is influenced by the skipped orbitals, and this basically makes calculations much faster. Of course, it doesn't end there, because my students are just very, very eager to implement new things, and they are very interested. And then one of my students approached me and said, well, we have somebody here in Aachen, Christoph Banwart, who implemented a semi-empirical method that's extremely fast. And can we use that? He implemented this XTB. It's a semi-empirical method, and I remembered back in the days, Simon Grabowski already told me that he would be very, very interested to try this. And now I was in a situation where I could directly talk to the people who developed this. And the key properties of this method are it's a covalent split, and I already know how to deal with covalent split from the other project. It's a polarized valence-only basis set, so it should be feasible to describe our systems. It has some anisotropic terms in the Hamiltonian to get accurate energies, and it only needs a few predetermined empirical parameters. So basically what happens is we just exchange the quantum mechanical software during the calculation. And Ben Ebel from our institute, he basically took on the endeavor of playing with this, and he had very, very unsatisfying results. Most calculation exploded when he tried to refine hydrogen atoms, and he got a little bit frustrated. Then he talked to Christoph Banwart again, and Christoph Banwart was a student in Stefan Grimme's group. And Stefan Grimme basically implemented an alternative, which is called PTB, not XTB. And PTB is basically aiming to reconstruct P, the density matrix of a system. And that was very, very interesting, because then we are back in the game of having accurate electron densities. And then we had to fit, of course, a new set of scattering factor correction functions. Basically, Ben is still in the process of finalizing them. This is the periodic table he presented me so fast, where most elements have an error of less than 1%, and only these heavy ones are left with some slight deviation below 2%, but we really want to have accurate results. So we are trying to finish this. I have to mention PTB does not allow F orbitals to be used, so lanthanides cannot be done yet. Maybe we will extend it in the future. But what results do we get? So for example, for sugar, the independent atom model gives 3.1% R value and this residual density. And if we use PTB, basically we have a calculation time of 0.01 second, which is incredibly fast in my opinion. The partitioning suddenly becomes the slowest step in all of this. And we have results that are quite nice, but how nice are they? So we compared it to the DFT calculation, and the DFT calculation in this case only gives slightly better R values, but it takes an order of magnitude longer for sucrose even. How good is so this is electronics, how good is the structure? The independent atom model, of course, underestimates, for example, OH distances. The XTB failed because it is not meant to recreate the density. And PTB got very close to DFT results. We also compared the ADPs of them. And basically what you can see is that the similarity index across most of the atoms is quite satisfactory if you use PTB compared to the DFT calculation. It's only the hydrogen atoms that are slightly worse. But I think this is, let's say, acceptable. The good thing about this is it also performs for heavier structures. So we can also use it on a cobalt system where the IAM in this case yielded this residual density. And I leave you to guess which one of the two is which. Only if you know what to look for, you can tell them apart. Of course, the left one is PTB because it doesn't really get the fine details of the electronic structure correctly. But comparing 300 seconds of calculation against 1 second of calculation is maybe a midpoint in between. So we can have results on an everyday basis. If you run the diffraction experiment, you can refine the structure on the go within a few seconds and maybe get your results. So on the go, learning everything in detail. What if we can learn the electron density? What if we don't need to calculate at all anymore because we can just guess? I said earlier that it basically boils down to this equation. And there's a wonderful lecture in this series by Michele Ceriotti, who showed us how we can basically try to transfer chemical environments from one place to another. So what we use is the SOAP descriptor, trying to learn the chemical environment from one system to another, and then interpolating the densities of already known structures onto new systems by basically using the Gaussian process regression model to interpolate between known data points and maybe even extrapolate. Lukas Seifert from my group, my PhD student, my second one, he basically implemented this workflow where you do conformer sampling of samples you want to train. You then calculate wave functions, train a model, and this can be used to predict the electron density and neatly interface into OLX2 and Nosferatu using analytical scattering factors. We can then do the structure refinement, and it basically yields results. If you compare to ORCA, where you need to calculate the wave function, partition, 400 seconds, you get results. And then if you use salted, in 42 seconds, you get the same results without having to wait for the entire calculation. And the neat thing about this is it's incredibly fast even for bigger systems. I'm sorry, somehow my screen resolution has changed here, so this is why this is on broken lines. But basically what happens if you take bigger systems, you need 5 seconds for this structure, you need 100 seconds for Crambine, and for lysozyme, you need 600 seconds. So what you end up with in the end is you have a linear scaling method of electron density calculation on your level of theory of choice that you trained your model on. So what we can do is quadruple zeta basis sets for training and then predict the electron density, and it scales linearly. Does it perform? I'm just going to give you the summary. Here you have the plot from the DFT calculations, and on the right are different versions of our salted model. It does perform. It gives good electronic structures. We have here the red crosses. They are maybe, to me as a colorblind person, also not great to see. But basically, even the cheapest model that we trained performed nicely. How stable is it against abuse? So if it didn't train on something, if you do something stupid, if you try to predict on something that it doesn't know. So we did an experiment where we trained a model only using different conformers of the cysteine molecule, and then we tried to predict the electron density of sucrose, which I would say is a slightly different chemical system that it should not be able to see. And it still outperformed the independent atom model considerably compared to the DFT method. Of course, we have to sacrifice some because it didn't see all the features it needs to predict. But I think this shows that it is also fairly robust against extrapolation. It's not that you can push it to elements it has never seen before. I mean, how should it know? But I think chemical space can be covered quite neatly using this method. And with that, I'm just left to thank all my collaborators, the people of the OLEX2 team, my previous PhD supervisor, my collaboration partners in all places all over the world, basically, the students of my group, Florian Meurer. It was great to work with you while I was in Regensburg, and it is great to continue having collaborations with you. For funding the DFG and the opportunity to develop code directly in the OLEX2 team is always amazing. And with that, I'm left to thank you for your kind attention.
Thank you, Florian, for a very interesting lecture full of detail. Now we have time for the questions. As I mentioned before, you can type your questions into the chat. I already see somebody typing. Yes. I'm one of the users of Nosferatu with high resolution data. Have you ever examined systems with agostic and anagostic CHM interactions with Nosferatu for better understanding of the nature of the CHM interactions? And what about metal hydride complexes?
This is a very, very good question. There was a study by Lorraine Andrade Malaspina and Simon Grabowski and more co-workers on some agostic interaction metal systems where we use this, and I would say you can use it in these cases to get an estimate of the elongation of the element hydrogen bond distance. In their case, they used it on a silicon hydrogen agostic-like interaction, if you want to call it that. I know the naming in these communities is quite strict, so I say agostic-like interaction. However, metal hydrides, there is a paper by Magdalena Woinska, who tried to look at metal hydrides and compared them against the neutron distances. And for metal hydrides, of course, there's not so much data in the CSD about neutron experiments on metal hydrides that are comparable. The interesting thing is that we have so strong residual densities around the heavy elements, the metal centers in this case, that usually the hydrogen atom kind of rides on the wave of positive and negative electron density if you refine these systems. So I would say those ones have to be taken with a pinch of salt at the moment until we resolve that issue of the residual density around these heavy metals. But I think still it is worth to keep pushing into this direction. So I don't want to disencourage anybody from doing this. I think we should be doing this, and we should be getting to the point of why we have these effects in the residual data and why we have these artifacts around the heavy elements that are not treated so far. Because if, in theory, we did all the absorption correction and all the corrections of the diffraction data correctly, they should not be there. So something, to me, something is odd there. So it should, in practice, be resolvable somehow, my opinion.
Thank you. That was a question from Reza Kia. And now we have another question from Hans Bedbirgi. How do different densities compare between the two models with the same R factor but different time requirements?
All right. So in the case of the effective core potential calculations, the difference densities are visually, I would say, nearly identical. There is some slight numerical differences, but I would say from the general trend where minima and maxima reside, they are more or less identical. In that paper, I published in the supporting information some comparisons, some direct comparisons between the two models as density cards, and the level of these differences is low. It's not zero because we make assumptions in these calculations. So you do see some slight differences, but I also would like to say at this point that if we make the assumption of a finite basis set, for example, at the cusp position using Gaussian functions, we also make approximations about that. So I wouldn't say that the Orca calculation is inherently more correct. It's just approximating at a different level, let's say.
Next question by Sunak Sarkar. Nice talk. I have this basic doubt about the iron complexes. How thermal parameters and occupancy of iron were deconvoluted during the variable temperature aspherical refinement, since they are highly correlated. Also, is there any plan to compare these results on mixed spin iron with neutron data to verify the accuracy?
Very, very good question. In these models, I think the displacement parameters between the two iron centers were restrained in order to be more or less similar between the two spin states, because we said they cannot deviate too much, but we didn't make them EADP because we said they might behave differently as they are slightly distorted in the bonding environment. So we restrained them in order to stay reasonable, but we didn't constrain them. So we think that we did a kind of good job. On the other hand, what we did is we did a scan of placing the different iron atoms along the axis of the distortion. So what we did is we made, or I say we, Daniel did this. Daniel made a lot of models where he placed the iron atoms at different distances between the two systems and compared how they refine. So we fixed the iron atoms at different distances and then tried to make models of that in order to get to the bottom of where is the actual minimum, or are we actually residing in, let's say, dangerous terrain of correlations and basically misinterpreting some results. But the reproducibility and the, let's say, disentanglement of this is a good question that needs to be answered if we want to make this a routine application.
How about neutron data? Is it possible to have a
Neutron
neutron
data.
data?
These compounds are stable, but I have not yet seen a crystal that would be big enough for the neutron diffraction experiments. I mean, you can grow them surely big enough, but for the time being, we focused on measurements on our X-ray machine. And so far, we have not tried to do neutron experiments because we do have the possibility of doing squid measurements to compare, for example, the magnetization as a ratio comparison of high spin and low spin.
A question from Julian Hen. Is there any other possible explanation for residual density between atoms in independent atom model refinement other than chemical density?
Is there any other possible explanation for residual density? Of course, there could be a plethora of causes that could lead to residual density. I think the electron density between atoms that we do not describe in the independent atom model naturally falls back to chemical density that we do not attribute because we make an over assumption in the model of spherical atoms. So in my opinion, taking care of this effect, if we can just calculate it, just as a reminder, we do not refine a charge density model in these methods. We just calculate the density from quantum mechanics and then use it in the refinement. We do not fit the data using these models. We still have the same number of refinement parameters in our model. So taking out something that we already know quite well from quantum mechanical bonding theory and quantum chemistry lectures from the bachelor's very early on, to me seems like a natural approach how to first deal with things that we know very well so that we can focus on the things that we do not know very well. For example, these residual densities around the iron atoms. And for example, the heavy elements like gold and mercury having these Fourier kind of ripples that we already always see in the residual density. So I think the other explanations for residual density in the IAM, I think when you can compute it as easily as in the case of Hirschfeld atom refinement, I would first focus on this before opening Pandora's box of looking into all the minute details between these atoms.
Question from Uli Englert. Thank you for nice talk. For the spin crossover system, you focus on what you called electronic figure of merit. Can you shortly comment on the geometric figure of merit in these cases?
All right. Thank you very much for that question, Uli. By the way, I still love your office. It's a very interesting question, which I think we have not yet tabulated. We have all the data, but I think we have not yet compared, for example, the geometric description between these high spin and low spin systems as a function of temperature. So I will put it down as a note actually to look into this. I think Daniel is also in the audience. He already hears what's coming to him, so that we can calculate the high spin and low spin optimized geometry, for example, and compare it against the refined data parameters. This would also then strengthen the point of the deconvolution of the atomic position of iron and the occupancy and displacement parameters. Yes, very, very good point. Thank you so much.
Razakia, thanks for the answering his question. Another question from Julian Han. For comparing residual densities from experiment and theory, you need to calculate F, structure factors from intensities for the observed intensities. These calculations include approximations. How much does the residual density depend on this approximation, and which are used?
Okay, how much does the residual density depend on these approximation? Of course, there's one which is always the elephant in the room. We use weighting schemes, and we use weighting schemes without worrying too much about them. I am totally on you with this point. We need to think about them more clearly. Obviously, the weighting scheme parameters in classical shell X type weighting schemes decrease drastically if you use non-spherical scattering factors, if you use TAM, if you use Hirschfeld atoms, if you use our resolution of identity atoms. The A and B parameters decrease drastically because now there's less residual in the data, so you need less adjustment of the individual weights. But this is one of the approximations that we use. However, they are used in the refinement. So we do not use the weight to calculate the residual density map. So the residual density maps are basically calculated from the scale factor that we fit in ULEX2 from the FOPS FCalc plot. We do not refine it as an individual parameter, but it's always just we get it from a linear regression of the FOPS FCalc plot. And this one is used in the residual density maps. And the other approximations are, of course, a Fourier algorithm, numerical accuracy of your computer, the completeness of your data set. So if you have incomplete data, you will also have skewed residual density maps. What else can I think of? So, of course,
negative intensities. They are
negative
abundant.
intensities can be a problem if you do not treat them correctly in the maps, and if you do not remove them, or they can influence. A problem is already a judgment. I would say an influence, and you have to be aware of what you put into your algorithm to understand what your algorithm produces for you as the output.
Another question from Hans Betbergi. When you look at the AD pieces, how do ADP
behave in the different models?
Behave in, yes.
So when we looked at, maybe I can go back to this slide. Let me see if I can. Luckily, I have enough screens. Anybody who has ever seen my offices remembers that I have a lot of screens always around me. If we, for example, go here, the ADPs, if we compare the different quantum mechanical methods, they differ only slightly, except for the case of Hartree-Fock. So ADPs usually differ not too much if you use all wave function calculation. As soon as you go to the PTB method, where we make drastic approximations, we start to see, of course, the scale here is a little bit bloated up because differences are not extremely large, but they are not negligible. So we have differences in the ADPs when we use these approximate methods. So if you wanted to have the most accurate structure description, you would need the most accurate type of calculation that you can do. I still think this general rule of thumb holds. However, if you want to get more than just your heavy atom positions, but maybe not sacrifice all the time of your calculation, you might get away with a slightly cheaper shot. Ideally, I would want this type of difference to vanish if you use these machine learned electron densities, which are as accurate as the full calculation, but as fast as the cheap methods. But for that, we need to, we did not yet publish this because we need to be sure that there's no way of this going wrong. If you use machine learning, you need to be aware of the dangers, and we want to test the dangers before we put this out for general use by everybody. So this is why we haven't published it yet. We are doing rigorous training and rigorous tests to see whether you can abuse it.
But I understand you also analyzed AD pieces.
We will also, so we are analyzing ADPs there, but this is not yet included in my slides because this is still ongoing training and work in progress. So pressure's on Lucas here a little bit. No, Florian, Hirschfeld differences along internuclear vectors. The Hirschfeld test still is something on my to-do list. I haven't implemented it yet. Sorry, Hans-Peter.
Julian Hen, thanks for the answer. And yet has yet another question. How much an R1 factor? of say 1.5% or 2%, you have shown R1 factors in this range, is due statistical noise, and how much is due to systematic errors?
Very good question. I think the easiest way to estimate this is trying to have a look at the distribution of residuals and let's say noise left in your data if you do a good measurement, if you do a high quality measurement, and trying to calculate a synthetic data set where you attribute a noise level that matches it in the end. So to get a feeling how by introducing statistical noise into your data, you can reach that level if you had a perfect structure to start with. And I think but this is gut feeling. For these organic compounds, if you have 0.8 angstrom resolution data only, you can get lower than 0.5% R1. If you have high resolution data, 0.5 angstrom, you have more noise in the data. So then I would say 1.5% can easily be the statistical noise level. So I wouldn't be surprised if this is actually a lot of statistical noise and the systematic error is comparatively small. I don't say there's no systematic errors left in the data. For example, absorption correction, detector count rate corrections, all of these things play into our everyday life of measuring data. But I think we are approaching more and more the level of having to fight these demons of unknown systematics and statistics.
If
Julian, thanks for the nice talk and answering the questions.
Thank you very much.
Can I have the final question? At certain moment, we were asking ourselves whether there is any, in quotes, magic combination of level of your basis set use, other parameters, treatment of environment, which would give us the best quality outcome from Hirschfeld atom refinement. What's your opinion? I mean, that definitely will be dependent on type of compounds we study, etc. But do you think, is there any route which we would suggest to users to follow?
My personal suggestion is we need to go away from Hirschfeld atoms. But this is, of course, not answering your question. If we are within the regime of Hirschfeld atoms, I would still go with a strong DFT method like R2scan or R2scan 0 if you need the hybrid part, and then a sophisticated, maybe triple zeta basis. Because if you have resolution of 0.4 angstrom in your data, there's no need to go quadruple zeta. There's no need to go to these very, very minute details. So I think with this kind of data, triple zeta, strong DFT method, I wouldn't go too hard on the Hartree-Fock contribution into your method, because then you get into this dangerous regime. But then we are in the regime where we have Hartree-Fock winning for organics. But for metals, I think you cannot just leave out the correlation. So I would say strong DFT, triple zeta basis, and you are on a safe bet. That's my gut feeling.
Thank you very much. Thank you for this excellent lecture and discussion.